Funding for this program is provided by Annenberg CPD to advance excellent teaching.
We've almost reached the end of our long journey through all of physics. And I must tell you, I have an embarrassing confession to make. And that is that we don't yet have all the answers. We do know that on the very small scale, the world is governed by the laws of quantum mechanics. And we also believe that on the very large cosmic scale, the world is governed by the general theory of relativity. But when those two great theories are examined very carefully, it's found that they aren't quite consistent with each other. And that means that we don't yet know the ultimate rules of the game. But my friends who work on that problem are very optimistic. They feel that very soon we will have the ultimate equations that describe everything in the universe. And so you might think that that will be the end of physics. When that day comes, that the final equations are written down, all physicists will be able to pack up their briefcases and go home and do something useful, like fix the plumbing or something like that. Well, imagine what we would have to do if we did have those ultimate equations of the universe. Presumably, they would be very difficult equations, probably differential equations, and it wouldn't be possible to write down all of the solutions just with a pencil and a piece of paper. You'd need a very large computer, and that very large computer would spew out an immense amount of output in the form of data giving all of the possible solutions of those ultimate equations. And then that really would be the end of physics, because we would have all of the solutions of the ultimate equations of the universe. Well, the fact is that all of that wouldn't do us the least bit of good, because those solutions would necessarily be at least as complicated as the universe itself, and we already have the universe itself. We would have learned nothing whatsoever from all of that. The real job of physics is not to find out everything. The real job is understanding. It's to find insight into how one thing is connected to another. It's to develop a kind of trained intuition that allows us to understand what's important and what isn't in any given phenomenon. What we want is to know why things work the way they do. Most of the work in physics is not spent in trying to find out how everything works. In fact, it's in doing exactly the opposite. It's in abstracting the simple out of the complicated, in making approximations, in making estimations, in trying to dig through complications in order to get your hands on the essential features of any given phenomenon. Today, we're going to look back one more time to see how all of that has been accomplished.
Every once in a great while, someone comes along and notices a pattern that no one had noticed before. The point might be, for example, that the planets in the solar system obey precise and relatively simple rules. Or it might be that the spectral lines of hydrogen obey a simple formula with uncanny precision. Perhaps it's the similarity between the flight of a cannonball and the orbit of the moon that catches someone's eye. Or it could be an arrangement of subnuclear particles that suggests their inner workings. Insights like these are never mere flashes of inspiration. They're the result of endless labor, trial and error, outright mistakes, and half-seen truths. And often, once accomplished, they become the subject of bitter controversy over who gets the credit. But this much is never in dispute. Once a new pattern has been discovered, and one part of the universe has been connected to another, the connection will never be forgotten. Such events are never the end of the story. Often, they're just the beginning. But what they begin may be nothing less than revolutionary. The tale of the mechanical universe began with the scientific revolution. Tired of the unwieldy complexity of ancient astronomy, Copernicus took the Earth from the center of the universe and put it in its place under the influence of the sun. And when the dust had settled, the result was a totally new view of the universe as a machine, a wondrously complicated machine, but one that followed precise mechanical laws. Knowingly or not, that idea is the silent foundation of all Western thought, from the time of Newton up to and including the present. But ironically, it's no longer believed by the very people who invented it, the physicists. And so the tale of the mechanical universe ends with the story of a second revolution. A revolution that occurred in this century, almost within living memory, and one from which the dust still hasn't settled. As with the first revolution, the second grew from an attempt to solve a problem. The first solved the problem of the solar system, and the second solved the problem of the atom. Could it really be that two such similar problems would require such radically different solutions, so that a second revolution would be required to overthrow the first? After all, the first revolution, the invention of classical mechanics, had not only solved the problem of the solar system, it had accomplished a great deal more. To begin with, it seemed to reduce all the phenomena in the heavens and on the earth to a single equation. A vector equation, to be exact, and a vector differential equation at that. But within its scope, it held the answers to a startling variety of questions. What's the principle of keeping perfect time? Or the secret of steering an infallible course? Why do ocean waves break on a beach? And why might a sturdy bridge collapse? With answers to questions like these, classical mechanics itself seemed to be a structure that would never collapse. Instead, it would inspire and guide the exploration of new realms. And in the long run, no expedition would be more fruitful, or strike with greater force than the study of electricity. Ben Franklin, with his seemingly endless talent for invention, gave the first useful account of electric charge. he provided the first explanation of a phenomenal 18th century invention called the Leyden jar. Of course, Michael Faraday was separated from Benjamin Franklin by a revolution, although not one of the scientific kind. Still, Faraday and Franklin did have much in common. They shared an almost perfect innocence of mathematics, an insatiable curiosity about nature, especially the nature of electricity, and a very considerable share of genius. And that's just what it took to connect electric charges with lines of force. The concept of lines of force would encompass magnetism just as well. And when Michael Faraday confronted the question of how magnetism could be used to create electricity, his answer, electromagnetic induction, would put the world in a constant state of changing flux. No one grasped the significance of changing flux better than James Clerk Maxwell. Maxwell had both a secret and a dilemma. The secret was that hidden within the forces between electric charges and the magnetic force between electric currents, nothing less than the speed of light itself was waiting to be discovered. The dilemma was that for all the elegance and power of the laws of electricity and magnetism, the laws of Gauss and Ampere and of Michael Faraday, there was something missing. And when James Clerk Maxwell supplied the missing piece, the idea that changing electric flux would produce a magnetic field, he had not only illuminated the entire electromagnetic spectrum, he had completed the science of electricity and magnetism. It was an accomplishment that rivaled Isaac Newton's invention of classical mechanics itself. As the 19th century drew to a close, Newton's classical mechanics and Maxwell's electromagnetic theory seemed to be the twin foundations of an edifice of physics that would stand forever. But it was a forever that was destined not to last very long. What could have been missing? It certainly didn't seem like much at the time. Just a few little details that didn't quite fit the big picture. For example, Albert A. Michelson had built a wonderful device to measure the motion of the Earth by studying shifting fringes of light. Just a small shift in the pattern, that was all that could be expected. But when Michelson twisted his interferometer in the ether wind, instead of the small shift he expected, there was none at all. Then there was the curious case of Max Planck. His problem was explaining the color of a hot, glowing body. And to solve his problem, he needed to introduce a new constant. It was a very, very small constant. In fact, Planck hoped it would vanish entirely. But it did not vanish. And then there was the strange story of Ernest Rutherford. When he bombarded a thin cold foil with natural alpha rays, the experiment worked almost perfectly. Nearly all the alpha rays sliced right through the foil, just as they were supposed to. Only a very few bounced back. But how could it be that any bounced back at all? From these modest beginnings, the new revolution arose, and no one played a more powerful role than young Albert Einstein. In the world of physics, the year 1905 in the life of young Mr. Einstein, he would submit his doctoral thesis in that very year, would be remembered on a par with the year 1665. That was the year that young Isaac Newton fled to rural Lincolnshire to escape the plague in London, and completed perhaps his most important work. But unlike Newton, who used his peaceful respite to find the answers to the revolutionary questions of the past, Albert Einstein, in 1905, made discoveries that really got the new revolution going. The problem of Michelson's interferometer could be solved, as Hendrik Lorentz had shown, if different observers measure different times and distances. But Albert Einstein went further, combining space and time into a seamless continuum. And Einstein's 1905 special theory of relativity was only the first step, not the last. Seeking to explain the age-old mystery of the law of falling bodies, Einstein would later conclude that space itself, or rather space-time itself, was curved, giving a new twist to the law of inertia. A new explanation of the force of gravity and a new theory of the cosmos. But we're getting ahead of our story. Back in 1905, Albert Einstein also noticed that he had a way to explain something called the photoelectric effect. Why should ultraviolet light discharge an electrically charged metal plate? It would if light came in bundles whose energy depends on frequency according to Max Planck's formula. The idea may have seemed innocent enough, but in reality, no manifesto has ever been more revolutionary. A century earlier, Thomas Young had first demonstrated the phenomenon of interference, proving once and for all that light was a wave. By the late 1800s, Maxwell's theory had explained how it all worked, as electric charges create light waves to propagate through the void. But the world of physics had barely sat back to enjoy its triumph, when Albert Einstein, refusing to ride the crest of the wave, said that light may be made up of particles. And that started the revolution going in earnest. Ernest Rutherford, that is. From the moment he realized that some alpha rays bounce back from metal foils, revolutions were exactly what Rutherford had in mind. Like Copernicus before him, Rutherford placed the nucleus at the center of the atom and set the electrons in motion revolving around it. Once long ago, the question had been, if the Earth is hurtling through space, why doesn't everything fly off? Now the question was, if the electron is constantly accelerated, falling forever in its orbit around the nucleus, why doesn't it radiate away its orbital energy and fall into the nucleus? Niels Bohr arrived with the quantum leap, and a part of the answer. Only special orbits would be allowed, those whose angular momenta were multiples of h bar, and light could be emitted or absorbed only in jumps between orbits. That's exactly what it took to explain the size and spectrum of the hydrogen atom. But what would it take to explain why those orbits and no others should be permitted? Prince Louis de Broglie was an aristocrat if there ever was one, but he also had the democratic spirit and a sense of equal opportunity. If light can be particles, he said, why can't electrons be waves? Electron waves would interfere constructively in just the orbits that Dr. Bohr had ordered, and that really spelled trouble. While seeming to march from one triumph to another, the very fabric of physics was unraveling, or to put it differently, the particle-wave duality seemed to be a badly mixed metaphor. Certainly, waves of differing lengths could be combined into a packet, or bundle vaguely resembling a particle. But then the particle wouldn't even have a definite momentum. In due time, this strange idea would not only come to be accepted, it would come to be known as the Heisenberg uncertainty principle. Professor Heisenberg's principle described in general terms the new laws of physics. The details could be found in solving a new equation. offered by Erwin Schrödinger. And when that equation was solved, it offered a picture of the atom far beyond even that imagined by Niels Bohr. The new theory, quantum mechanics it was called, would explain far more than the states of the hydrogen atom. It would account for all the other atoms of all the other elements as well. Quantum mechanics may well turn out to be the ultimate triumph of physics. But like many triumphs, it was purchased at enormous cost. It challenges the most fundamental idea of all, the connection between cause and effect. In Aristotelian physics, every motion had to have an immediate cause. It took impetus to keep a cannonball moving. In Newtonian physics, motion no longer needed a cause, but every change in motion did. In modern physics, however, a given cause doesn't always produce the same effect. This is the real departure from the past. The results of a given set of circumstances are not completely determined. There are alternative possible outcomes. Only the probabilities of the alternatives are precisely determined. This lack of determinism is truly revolutionary, and it's not to be confused with a similar situation that arose in Newtonian physics. Statistics have long been used to describe the motion of molecules in a gas, but that was just a convenience. Theoretically, the path of each hard little ball could be calculated. Theoretically, the future of the universe could be predicted. It just wasn't practical to do it. But with quantum mechanics, the situation has changed fundamentally. As a matter of principle, the courses of atomic particles cannot be predicted precisely, and the future of the universe is not predetermined. Revolutions occur in the affairs of nations, as they do in the fields of science. They come, they go, and more or less things remain the same. Even in the quantum mechanical universe, some things haven't changed. Energy is conserved, as it always has been. And so is momentum. And angular momentum as well. In fact, those very ideas reside at the very heart of modern physics. For example, in the theory of relativity, momentum is conserved, even if that means that mass must increase with speed. And that's precisely why energy is equal to mc squared. Even Niels Bohr, bold as he was, didn't challenge the idea that energy is always conserved. And the idea of energy remains fundamental, even to the fundamental particles. And as for angular momentum, the idea not only guided Niels Bohr, it emerged as a central concept of the new physics, in which each electron, to say nothing of the other elementary particles, is a kind of quantum mechanical gyroscope. And yet, it's hard to imagine any change more profound than those brought about by these two great revolutions, just a few hundred years apart. First, the crystal spheres of the ancients were transformed into the rational, orderly, perfect machine, the mechanical universe. And then, in a breathtaking turn of events, time and space, matter and motion, the very pistons and gears of the great machine itself, were transformed beyond recognition. Welcome to the quantum mechanical universe.
Well, this is the moment you've all been waiting for. Our long journey together through all of physics is finally finished. But there's just enough time left for one last look over our shoulders at where we've been. The story all began, of course, with Copernicus. He gave a little shove to the Aristotelian system, and the whole thing tumbled down. 150 years later, it had been replaced by the Newtonian worldview. And even today, all educated people still think about the world in that way. Well, not all educated people. It turns out that scientists no longer think that way. In our own century, in fact, practically within living memory, there has been a new scientific revolution, and Newton's laws are no longer the law of the land. Well, that raises an interesting question, and that is, if we no longer believe Newton's laws to be true, why did we spend so much time teaching you about it? And a related question, is this new revolution a similar one to the original one in the sense that wrong laws have been replaced by right ones? The answer to both questions lies in the fact that Newton's laws are really just as true as they've always been. The moon still falls 1/20th of an inch every second, just as it always has done. What we have found out is that Newton's laws are not the ultimate truth. They arise out of even deeper laws, even more profound laws. But there is a sense in which this new revolution is similar to the one that came before it. And that is that there's been a change in the kinds of questions that we ask. In the first scientific revolution, disputation over the interpretation of human or divine authority was replaced by observation, by measurement, by the testing of hypotheses, all of it with the powerful help of quantitative mathematical reasoning. And the result of all of that was the mechanical universe. A universe that inexorably worked out its destiny according to precise, predictable mechanical laws. Today, we no longer believe in that universe. If I know the precise position of some particle at some instant of time, I cannot have any idea of where it's going or how fast. And it doesn't make any difference at all if you say, all right, you don't know where it's going, but where is it really going? That is precisely the kind of question that is scientifically meaningless. That is the nature of the world we live in. That is the quantum mechanical universe. Well, for once, I can't say, I'll see you next time. What I can say to you is, goodbye and good luck.
Meow, meow, meow.